This is Mrs. O'Neill for AP Chemistry, Chapter 19, Section 6. Free energy and temperature and how they relate to each other. So you should have watched the first intro lesson on spontaneous processes. So here are my notes. Again, a spontaneous process is only going to be spontaneous in one direction. In the opposite, it will be non-spontaneous. Gave that nice little flow chart, and again, here are your positive and negatives and what that means as far as a reaction and how this is going to relate to the equilibrium constant. So the process recap, again, spontaneous reaction, what happens, and in a non-spontaneous reaction, what happens. And again, look at those signs. Later on, there's going to be charts that he shows you, and also in your notes, there's going to be charts as far as positive, negative, and then if it's high temperature or low temperature, and that's going to play a part. So again, spontaneous reaction will also be called thermodynamically favored, and we talked about that before. I've used that term before. And again, so it doesn't matter how fast or slow a reaction is, it just depends if it's spontaneous or not spontaneous. Is it thermodynamically favored or not thermodynamically favored? So in the AP exam, every time you see the word spontaneous in the book or on the AP exam, you should say to yourself, thermodynamically favored. Yes, thermodynamically favored, thermodynamically favored. Got it? Okay, good. The nice College Board folks won't give you credit for the S, spontaneous word. They find those responses to be unfavorable. Ha ha ha. So you really don't want to use the term spontaneous on the exam. You want to talk about how that process or that reaction would be thermodynamically favored. Why? Well, let's look at H and S. Again, H would be enthalpy and S is entropy. Is it exothermic, endothermic, and is it going to happen on its own, right? Delta S tells us if it happens on its own. So how is this all related to that equilibrium constant? Again, that equilibrium constant is products over reactants. So he also did spontaneous, a simulation. And again, you might want to go through that if you get a chance. And you should take a little bit more notes on the process and how he went through how those two are related to each other. So he said in a non-spontaneous reaction, K would be less than 1. At equilibrium, K is equal to 1. We already know that. And K would be greater than 1 in a spontaneous reaction. So again, we have a lot of equilibrium reactions, especially when we deal with weak acids and weak bases. So we have to know, is that reaction going to be spontaneous or not? So again, a spontaneous reaction and what those values would be, and a non-spontaneous reaction and what those values would be. So here's a little chart that he gave, which I thought was pretty neat. So again, a negative delta H and a positive delta S would be spontaneous, but a positive delta H and a negative delta S would be non-spontaneous. So you should have also watched the second intro lesson, and he was talking about using this Gibbs free energy. So again, it's the available energy to do work. And he talked about how potential and kinetic energy, right? So you have the potential energy to have the kinetic energy for that ball to roll down. And doesn't this look familiar? Doesn't this look like that graph that he showed you before where you had reactants on this side? Here is delta G equals 0 at equilibrium, and here we would have the product. So it should look familiar to you. Voila! Reactants yields products, and on the very bottom, it is at equilibrium. Spontaneous or not spontaneous? That is the question. So again, delta G, there's your signs, positive, negative, and 0. I guess I should say it the other way. Delta G negative would be spontaneous. Delta G positive would be non-spontaneous. Gave another nice flow chart and said, are these spontaneous processes? So again, this would be spontaneous. Delta H positive only if delta S is also positive, if these two are positive, but it has to be at high temperatures, and that's where that T comes into play in the equations. So you can have a positive delta H and a positive delta S, but then your temperature has to be high enough in order for it to go in a spontaneous reaction. Here we have a negative delta H and a negative delta S, and again, it can be spontaneous, but then the temperature has to be low according to that equation. So there's your example again. So how about these cold packs? Again, you have a positive delta H in a cold pack, right? That's an endothermic process. And what happens is your solids are moving into ions. So you have an increase in disorder. But here we have 1 mole of solid going to 2 moles of ions. And it's going to end up being a spontaneous reaction if we plug and chug into the equation. Okay, so now on to your notes packet. So in this section, you're going to consider how relationship among free energy change, enthalpy change, and entropy change provides insight into how temperature is going to affect if the reaction or process is spontaneous or not. So pause the video. I don't think there's anything actually here to write so far, but just as a reminder, you always want to pause, fill in the blanks, and then play to hear my words. So again, don't memorize. Please don't memorize. Use the equation. So I like to remember that delta G and delta H should be the same sign in order for the reaction to be spontaneous, and delta G and delta S are opposite signs. So one way I like to look at this is here's our positive, right? There's no sign in front of the delta G, and there's no sign in front of the delta H. So those two should have the same sign, where here you have that minus H delta S, so it's going to be minus delta S. It's opposite. S is going to always have that opposite sign to say that it is spontaneous. Okay, so again, just as a reminder, really we're adding the negative of T times delta S. So just so you can remember that. And again, it's going to help me know that that delta S is opposite because of that negative sign or that minus sign. So here, can you predict from the sign of H and S if the reaction is going to be spontaneous or not? And again, this information is very useful to just understand the signs, but you also have to take into consideration the temperature. So this is a nice quad, if that's what you want to call it. Again, to just think of it like on a number line and where all of the positive and negatives are. This is also a nice graphic to show you, again, if it's positive, negative, and what delta G is going to be, positive or negative, spontaneous or not spontaneous. So here's going to be a whole bunch of scenarios or cases. Again, I'm going to suggest these are not in your notes packet per se, but it just gives you a better understanding of how to deal with delta H and delta S and with that temperature as well. So I would kind of pause the video and just read over it. I'm not going to actually talk too much about these because it's information on this equation helping you to understand that relationship. And here's again more information. Again, I got this, I believe, from the AP community that I deal with online. And again, they're trying to tell you don't memorize what's going on. Try to understand the equation. So take a moment to read over these couple of slides. And again, some more visualizations of understanding what is going on with delta G and the signs of delta H, delta S, and of course the temperature at which the reaction happens or the process. And here again is an overview of the HS and then that negative T delta S, okay, and that's where you're bringing in the temperature, and of course the delta G overall, and the reaction characteristics, if it's going to be spontaneous or not, high or low temperatures. And here are just some examples. So 3 ways to calculate delta G. The delta G equals delta H minus T delta S. Again, that's on your reference sheet, and it's really useful, especially if they give you the values of H and delta S automatically. You could also add up the delta G's like we did way back in the day with Hess's law. So if they give you a whole bunch of reactions and different delta G's of each reaction, you're going to do very similar to what you did in chapter 5 with Hess's law. And of course, that ultimately products minus reactants, they can give you those G values, and you would do products minus reactants. Let me go back to this real quick though. Again, I want to remind you that S is in joules. G is going to be kilojoules, H is going to be kilojoules, but S is going to be in joules. So you need to remember that when you need to convert from one unit to another before you deal with that equation. Give it some thought. Hopefully that makes sense, again, dealing with those signs and that equation. So let's recap. I believe this is in your notes. So I kind of numbered them so you know which way we're going, and see if you can kind of come up with the answers as we go along. So what is delta H? Enthalpy, right? That heat transfer, the heat energy. If it's positive, it's endothermic. If it's negative, it's exothermic, and kilojoules per mole. S, on the other hand, is entropy, and that's disorder. If it's positive, we're increasing disorder, right? That's how nature wants things to happen. So that's going to be more on the positive, spontaneous side. And if delta S is negative, it's going to be a decrease in order, and there's your units of joules. Delta G is your Gibbs free energy, or if the reaction itself, the process, is going to be spontaneous. Positive means that it's not spontaneous. Negative means that it is spontaneous. So again, here we have delta H and delta G being the same sign, negative, negative. And here we have S, positive, is going to be opposite sign. And again, this is going to be kilojoules. So you want to take note that S is the only one in joules, so you're going to have to convert those units. So hopefully that makes sense to you guys, and we'll see you in class and answer any questions.